Hello, everyone. My name is Jiangsu from Sanyashan University. I'm here to present handling heavy-tailed input of transformer inference on GPUs. Transformer was introduced in 2017 by a team at Google Brain and are increasingly the model of choice for natural language processing problems, replacing recurrent neural network models such as long short-term memory. Transformer claims two main structures called encoder and decoder, which leads to the development of many pre-trained systems such as BERT and GPT. These models are called transformer-based models, achieving superior accuracy for many NLP tasks. A transformer-based model basically includes the embedding layer, multiple encoders or decoders. Each encoder or decoder is further made of self-attention mechanism and leader layers. Here, we mainly take BERT as an example, and it is composed of multiple encoders. For the embedding layer, it is responsible for representing the input sentences into vectors. Each vector is represented as a vector, which includes the position information in a sentence, segment information, and the word meaning. In transformer-based models, multiple self-attention heads are packed and work together, which is called multi-head attention. After the word embedding layer, a sentence becomes a matrix, and each row of the matrix represents a word. In practical, multiple sentences are batched for better hardware efficiency. As the lengths of different sentences are variable, sentences will be padded into a fixed length. For a single sentence in a single head attention, the detailed computing process is as in this figure. The sentence matrix is multiplied with 3-parameter matrix and gets Q query, K, K, and V value. Valid values are colored, and invalid values are in blank. Then query matrix will be dot multiplied with K matrix and get a square matrix, which the process is called QK. Here, each value of the resulted square matrix can represent the relationship between two words. Then the square matrix will be dot multiplied with the value matrix to record this relationship, which the process is called QKV. Then the result will be sent to leader layers. The leader layer also suffering from the redundant computation problem. Uneven sentence lengths in a batch lead to the redundant computation problem. We further investigate the length of sequences in 8 corporal of the GLUE benchmark, which is a widely used dataset collection in the NLP field. To demonstrate the statistical result, we remove outlier sequences with extremely long lengths and cluster sentence lengths with 32 as a thread. The figure shows a normalized result, and we connect scatters of the same corpus to give a clear view. It illustrates that the lengths of sentences in the same batch generally vary a lot, and the meaning concentrate on the short length area. In other words, the input sentence lengths of NLP tasks follows a heavy-tailed distribution. For leader layers, multiple input samples are batched as input. Then each row, or rather each word, will multiply with the entire parameter matrix. If sentences are padded into the same length, there exists redundant computation in leader layers of transformer-based model inference. The self-attention mechanism is a key idea of transformer-based models, as shown in figure, for the word eat. the word the and the word animal are the most related words. At a high-level understanding, the self-attention mechanism can enable the learning of the relationship. It helps capture the dependency between any two words in a sequence. With padding, matrices for all sentences are the same. In NVIDIA GPU, the Kublas function, Kublas GM strated batched, is adopted. However, with this function, here are large amounts of redundant computation. In this figure, less between matrices represents that these two vectors will be multiplied in the padding strategy, which only red lines represent the computation between two vectors are valid. We can notice that the number of black lines largely exists side of the red lines, as claimed above. The lengths of sequences in the same batch generally vary a lot, and they mainly concentrate on the short length area. So here are plenty of redundant computation in QK and QKV functions. To handle the heavy-tailed input of transformer inference, we introduced a unified solution for eliminating most redundant computation. The unified solution includes three strategies for the self-attention module, the NLP module, and the entire model respectively. As shown in the overview, the fine-grained strategy orchestrates the fine-grained parallelism of QK and QKV functions and removes the redundant computation of the self-attention module. For removing the redundant computation in the linear layers, we take the common word accumulation strategy, which arranges sequences within a batch densely. Then, instead of the batched padding and related data layout switch, we design the block-organized strategy to unify the fine-grained strategy and the word accumulation strategy from the view of the entire model, with which the overhead of the data layout switch is reduced. To eliminate the redundant computation in linear layers, we take a simple idea from the previous work, and we call it the word accumulation strategy. It accumulates words in different sentences together, or rather switch the padding data layout to densely arranged data layout. As there is no data dependency between words, the redundant computation can be removed. The fine-grained strategy adopts the idea of block matrix multiplication and illustrates the potential fine-grained parallelism. The basic idea is to calculating the execution order of valid mini-block matrix. You can look in the picture. These red dashed boxes are mini matrix, mini block, and we record the order of these mini block matrix multiplications in the index arrays. Then, following index arrays, GPU can perform the self-attention module without most redundant computation. Besides, as the self-attention mechanism repeats multiple times in a transformer-based model, there only generates index arrays once and can be used multiple times. Through accessing index arrays in order, GPU knows which pair of valid mini-blocks should be processed next. For a pair of mini-blocks, it is actually the matrix multiplication. Thus, each vector in the first mini-block will be multiplied with all vectors in the second mini-block, indicating that each vector in a mini-block will be accessed multiple times. In this way, we can adopt the structure of advanced GPU, the shared memory. Shared memory is a powerful feature. It is much faster than local and global memory in terms of both latency and throughput. Besides, the shared memory can be controlled by programmers. In this way, it's attractive to reduce memory access overhead through prefetching the data of mini blocks from the global memory to shared memory. Initially, we simply immigrate the mini block data from the global memory to the shared memory as the left part of the first figure. After immigrating data to the shared memory, centralize all threads in the block and start the computation. However, a direct copy from global memory to shared memory generally has very limited benefits. In order to gain high memory bandwidth, shared memory of each SM is divided into 32 memory blocks in equal size, corresponding to the number of threads in a warp. For instance, two adjacent values will fall in two banks. However, if multiple requests fall in the same bank, bank conflict occurs, causing the request to be serially executed multiple times, and largely reducing the efficiency of shared memory bandwidth. Notably, bank conflicts only occur among threads in the same warp. In this way, the naive copy results in severe bank conflicts, as in the left part. To serve it, we adjust the data layout in the shared memory and make threads in the same warp access data in different banks. As shown in the right part, the mini block is transposed when immigrating data from the global memory to the shared memory. In this way, threads in the same warp won't access data in the same bank, and the shared memory bank conflicts are eliminated. Next, for fine-grained strategy, there is atomic problem. So we have the efficient atomic operation. As in the left figure, results of multiple mini blocks pairs in the two-dimension partitioning will write to the same place. Thus, the correctness of the fine-grained strategy needs to be ensured by the atomic operation, in which the contention problem degrades the performance. To reduce the overhead of the contention problem, we take several optimizations. First, from a general view, we reduce the overhead of the atomic operation by reorganizing the offsite generation and enlarging the write interval between values which are going to write in the same place. In detail, the offset generation function has multiple loops in different dimensions. We can adjust the order of loops and enlarge the write interval of two dependent values to alleviate the contention problem. Further, for the QK function, as query and K are the same in shape, the query function, query matrix and the K matrix are the same in shape. We can degenerate the mini block indexed to a more special case. As shown in the right figure, we use 1D partitioning, one-dimension partitioning. With the one-dimension partitioning, a place in the output matrix only corresponds to a pair of mini blocks. In this way, the computation of QK function can remove the automate operation completely when implementation. Until now, if we use the word accumulation strategy, we can remove the redundant computation in the leader layers. And if we use the fine-grained strategy, we can remove the redundant computation in the self-attention layers. However, the word accumulation strategy requires the dense arrangement data layout, like this. The dense arrangement has no padding between sentences, and the densely arranged matrix will be put into GMM. However, the densely arranged data layout cannot support our fine-grained strategy of the self-attention module, as these valid mini-blocks still invade into valid values and make the little redundant computation. To support the fine-grained strategy, we can follow the data layout of the batch padding layout. Yeah, like this, the batch padding, as in the bottom of this figure, in which all sentences in a batch are padded into the semblance. In fact, without taking the word accumulation strategy into account, the batch padding layout will not introduce any overhead in performance. However, since the leader layers connect to the self-attention layers, the densely arranged layout and the batch padding layout becomes incompatible. To unify these two data layouts, we can take data movement and switch between the densely arranged layout and the batch padding layout, introducing overheads. To reduce the data movement overhead, we organize the data layout of the self-attention layer in the green of block. Here we call the block padding layout, like this, block padding. The block padding only pads essential values required by the fine-grained strategy of the self-attention layers. In detail, the fine-grained strategy splits valid values in blocks. If the size of valid values cannot be divided, blocks on the edge require to be padded. Thus, the block padding only pads blocks on the edge, which has much less padding area than the batch padding. In comparison with the previous densely arranged layout, the block padding layout still has different shapes and requires data movement to become compatible. While comparing with the batch padding layout, the padded area can be largely reduced. In this way, although there still requires to switch from the block padding layout to the densely arranged layout, the data movement overhead becomes less in GPU architecture. Moving on to the performance evaluation section, here we select two popular transformer inference framework. It's a turbo transformer from Tencent and the faster transformer from NVIDIA. In comparison, as turbo transformer and the faster transformer both use a cuBLAS library to compute QK and QK wave function. We take the cuBLAS library as a baseline. This is the latency of computing QK and QK wave function of processing 8 corpora. Since all self-attention modules in a transformer-based model have the same shape and behavior, the offsite generation process will be only executed once per batch. Besides, as we generate the index in host, the time can be hidden with the word embedding module in the practical inference. Here, the index array building time is included. For the cuBLAS implementation, as in the figure, we investigate that the couple with the same fixed length have a very similar latency. Here the fixed length is the longest length to be padded in a corpus. As the fixed length doubles, the latency grows severely, for it is a quadratic relationship between sequence length and the computation amount. Moving on to our fine-grained kernels. The latency mainly depends on the average length of a corpus. Typically, comparing WNLI with SSTB, as WNLI uses a smaller sequence fixed length than SSTB, the latency of the cupola strategy is much lower than that of SSTB. However, the latency using the fine-grained kernels is similar to that of SSTB. You can look at this picture. Here is a 3 and here is a 10 for cupolas. However, for our fine-grained kernels, it is similar. Of course, for example, WNLI, the latency using the fine-grained kernels can even exceed that of the cupola kernels in some cases, performing a negative optimization. Here we compare our strategy with our block organized strategy with batch padding strategy. The batch padding strategy are used by both fast transformer and turbo transformer. They have different implementations. As turbo transformer computes offsite in the kernel function, and there exists condition statements to judge whether a value is redundant. It performs the worst in almost all cases. But for faster transformer, it has a similar, only a little worse performance with our strategy. This is because it also built indexed before data movement, and it only processes this valid. It only moves this valid data. Overall, our method displays advantage in most cases. For the fine-grained strategy evaluation, it is only for the self-attention module, and here for the overall performance, here are self-attention module and linear layers. As the fine-grained strategy contributes the most in latency reduction, here overall latency displays a similar trend. But since there are computation of linear layers, and the linear layers is not optimized, the speed up looks less. Okay, the computation amount of linear layers has a linear relationship to sentence length, and the computation amount of QK and QKV has a quadratic relationship to sentence length. In this way, for this corpus with longer fixed length, our solution performs better. Okay, thanks for listening.